Good afternoon. Will, darling, hi Will. You're definitely not expected. Who else we got? Say hi so I know you're there and let me know you can hear me as well. Can't just be me and Will. Yes, 6 likes. YouTube sensation. Will can hear me. We got Harrison as well. Do you actually have anyone who's in my actual class rather than just random sort of people? I mean, you're welcome. But oh, Hannah. Sadie again. Not in my class, but fine. While I'm waiting for other people to check in and say hi so I know who's here, people who aren't in my class, we're kind of doing the work that I set for my class. We're going through these answers. So you may or may not find this useful if you haven't done that work. Alicia, hi, or A, whatever that means. Oh, Sadie's changed her mind. Ellie, hi Ellie. Hola, international, like it. Subscribe. I think you have to say that because everyone says that on YouTube. Keem, sup, wagwan. Right. Let's get going, shall we? So we've got these questions, and hi Jess, we have a variety of scores going on with these. I've got paper and mini whiteboards all over the place, so if I keep looking away, excuse me. First ever YouTube video. You can say you were here at the beginning. So without further ado, this first question, what we've got here is this. Let me just remind you. Okay, and I don't know if you can see this at the same time. That's why I sort of printed it out. A bird sits on a rod. There are wires P and Q. The rod has a weight W and is 15 centimeters long. The weight of the bird 2W at a distance X. I'm going to sketch that out on here very quickly. So bear with me while I do a really rubbish drawing. We've got P and Q. And we've got a total length of 15 centimeters. We've got a bird that looks nothing like a bird with a weight of 2W. The rod itself has a weight W, and the bird is a distance X away. So we've got something like this. So the bird's 2W, the rod is W, 15 centimeters across here. What is X? And what we're told is that Q has a tension that's twice as great as P. So my method for this one would be obviously to take moments. We're trying to find X. And what we want to do here is, I would just give numbers. So we don't know what P or Q are, but what we do know is that Q is twice what P is. And what we also know in these questions is that everything weighing down has to be equal to everything going up. Okay, so what I'll probably do here is assign Q as having a weight of 4, a tension of 4, should I say, and P 2. You could have chosen any numbers. I've just chosen easy ones because we're told that this is twice the tension of this. So 4 and 2. That means I've got 6 going up in total. And what I know down here is I've got to have 6 weighing down as well, and that the bird is twice the weight of the bar, which will make the weight of the bird 4 and the weight of the bar 2. Bird 4 and bar 2. Okay, so Now what I'm going to do, and I'll keep sort of flicking between both boards, is take moments, and I'm going to take moments around point P. What do I mean by that? What I mean is that we're going to take P as the pivot, and everything else here is pivoting around P. So what's going up? We've got 4, that's what we assigned Q, times 15. So I'm going to write that on my other board. I'll show you this in a moment. 4 times 15, that's the only thing pulling this up. That is going to be equal to my moments going the other way, which is 2, that's what I've assigned W to be, times 7.5, that's half of the length of the bar, plus 4 multiplied by X. So I've now got this. Okay, this is the tension in Q times the whole length. That is equal to the weight of the bar times half the length plus the weight of the bird times X. From here, once you realize I've done it by putting numbers in, you'll probably get it anyway. All we're going to do is just tidy this up. So 4 lots of 15. Let's see if I can get somewhere where you can see. We've got 60. We've got 15 there, 2 lots of 7.5. And we're adding to that 4x. Take 15 from this side. 45 is equal to 4x. So x equals, let's just do it, 11.3. Okay, so I'll just leave it there for a second in case you're looking at that. That gives us answer C. Hopefully that makes some sense. Question 2. Okay, question 2, where are we? There. Immediately after takeoff from the Earth, space shuttle. I'm trying to read this backwards because for some reason my screen is backwards. Yours is probably the right way around. It's a whole new world. YouTube. Backwards screens. Immediately after takeoff, a rocket has a mass 12,000 kilograms, accelerates vertically upwards at 1.4. Right. This is pretty straightforward. So we've got a rocket, we know its mass, we know its acceleration upwards. We had a question like this in class the other day. The mistake was people were just using their SUVATs or using F equals ma based on that acceleration they've told you the rocket's going up with, forgetting that it always has an acceleration down of 9.81. So when a rocket takes off, no worries, CJ, forgot the weight of the bar. Back to question 2. When that rocket takes off, it doesn't just need the force to get that acceleration upwards. It needs a force to overcome the acceleration downwards and have enough left over to accelerate the rocket upwards. So what we're actually doing for question 2, we are saying, let me just rub out some of this working. I've only got a limited whiteboard space here. We are saying, yes, it's got the acceleration 1.4, but it's had to overcome the acceleration 9.81. That gives me actually an acceleration in total needed of 11.21. When you have that, you do what most of you probably did and put that into F equals ma. This is the mass of the rocket times 9.81. Sorry, apologies. This is what we're trying to work out. This is the thrust. This is the mass of the rocket. This is 11.21. When we do our 12,000 kilograms for the rocket multiplied by 11.21, what we get is 1.3 times 10 to the 5, which is answer C. Hopefully that makes sense as well. So remember, the overall thing there you're forgetting is, yes, we can accelerate something upwards, but you've got to add on the force needed to overcome that 9.81 meters per second squared of acceleration as well. Coffee. Oh, also, I forgot my lanyard. Right. Question 3. A uniform meter rule. Hopefully you weren't thinking, how long's the ruler? Meter rule. Weight 1.5 newtons, pivoted 15 centimeters from one end for use as a balance. And this was the diagram. We actually did this one in class the other day. The idea here is taking moments again. Essentially, we're given the weight of this pan, but not the object that's put in the pan. We are given the weight of this, and we have got all the distances that we need. So for this one, we are going to take moments from the pivot, first of all, of the side that we know. So that's going to be a 2.5 Newton weight multiplied by 60 centimeters. We write that. (2.5 times 60). Have I got anything else on that side? Yes. This is where CJ may have forgotten the weight of the bar again. The weight of the bar is going to be in the middle of the bar, somewhere here. Now the weight of the bar, we were told, is 1.5 newtons. So we've got 1.5 newtons. What's the distance? Well, we know that it's 50 centimeters along the bar because it's a meter in total. We just need to take our 15 centimeters off that. So it's going to be 35 centimeters. So the other moment we've got is 1.5 newtons times 35. So that's everything that we've got going in a clockwise direction. Look at the diagram. Clockwise. Okay. Anti-clockwise, the way I would do this question is, let's just work out the weight of the pan and the object. I know they've given us the weight of the pan, but if we just treat this as one thing and then we just take the weight of the pan off afterwards. So we know that this weight W here times 15 is my anti-clockwise. So everything I've done here is equal to W times 15. Okay, we rearrange and neaten up all of that. So we've got 2.5 times 60, that's 150. 1.5 times 35 is 52.5. Use a calculator if you need to. That's all equal to, so I'm struggling to write on this board, 15W. Add these two together, divide by 15, and you find that W is 13 newtons, which is answer C. So again, it's clockwise equals anti-clockwise. Always that method. You forget the weight of the bar again there, CJ. At least you know where you're going wrong. Right, where are we? Question 4. Question 4. The car is moving up this ramp here at a constant speed, and we want to know what is that steady speed. So something moving up a ramp. Just clean this board. The equation that we're going to try and use here at the end is power equals force times velocity. Okay, so let's just write that. P equals FV. So that's what we're aiming to use. However, we want V. We know the power of the car, that's given in the question. We don't know what the force is that is required to keep this car going at this velocity. That force is going to be the force that equals the weight of the car down the ramp. So this car, obviously, if you were to take all forces off, it would roll back down the ramp. So we want the engine to provide a force that's going to keep it going up the ramp, okay, but at a steady speed. So friction is obviously trying to stop it. Weight is trying to pull it down. You've got to get that steady speed between the two. How can I work out that? Well, it's simply a case of car going up a ramp. It's simply a case of whatever the weight of this car acting down the ramp is, that's the force the engine needs to provide up the ramp, and then it will go at a steady speed. Remember, weight goes like that. If this is one component, the one we're trying to work out, that's the other one. We're not bothered about this one in this question. We've got these three forces here. You could put those into a triangle if you want to. So you've got your one down the ramp. You've got your, struggling to see this one at the same time as draw it. So you've got this one going down the ramp here. You've got your weight of your car, and you've got your one going into the ramp. The angle there is the same as that angle there, which in this question is 12 degrees. And if you label all these sides and do your trigonometry, you'll get to something that equally you could learn. I said this the other day. If you want to work out the force down the ramp, the weight down the ramp, we are going to use sine of the angle. If you want to work out your weight into the ramp, use cos of the angle. Just remember those if you want to, just as a quick one for exams, okay? So down is sine, I don't know, slide down the slope, sine, something like that. Crush into the slope, cos, however you want to do it. So W, the weight of the car, sine 12 is the calculation we want to make here. The weight of the car being, well, it's 950 kilograms, but we need to multiply that by 9.81. So, having difficulty with pens here. 950 times 9.81, all multiplied by the sine of 12 degrees. That will give me my weight down the ramp. Okay. When I've done that, that actually comes out at, because I did this earlier, 1937 newtons. Again, use common sense. The car is 950 kilograms. You're multiplying that by 10, so you've got nearly 10,000 newtons of weight in the car. Is most of it acting down the ramp, or is most of it acting into the ramp? Well, it's only 12 degrees, so most of it is acting into the ramp. So I would expect this to be quite a small fraction of 10,000 newtons, and it is. Okay. Once I know that, I can then put that into P equals FV, because I'm given the power of the car in the question. The power of the car is 6.5 times 10 to the 4. That's my power. I'm going to divide that by the force I just calculated, 1937. This is great fun trying to write a horrible angle into a backwards camera. When I do that, come out with 34 meters per second. Just to prove that one to you, where's my calculator? Just do that final calculation there. So we had 6.5 times 10 to the 4. That was our power, which we'd given in the question. dividing that by 1937, which is the component of weight down the ramp that we calculated. Boom. Answer to the question, which was C. Next, question 5. Easy one. Most of you got this right looking at the sheet. Which row correctly states whether momentum, mass, and velocity are scalar or vector? Momentum is a vector. I've got this printed on 2 sheets split down the middle. Momentum is a vector, mass is a scalar, velocity is a vector, which means that the answer is D. Question 6. Am I trending yet? I would like to think I am. Projectile. What is the time taken for this projectile to reach the ground? That's the question. Okay. Now, the shortcut here, when we're not taking air resistance into account, which we never do in our questions, this parabolic path we can assume is symmetrical. So however long it takes to get to the top, it's going to take the same amount of time to get down to the bottom. Okay. So I just want to work out the time taken to go to a maximum height and then double it. What do I know about this? Well, I know the speed it's going at, but that's along a tangent to the curve. If I can work out and just deal with the upwards movement, I can work out the time taken to get to the maximum height really easily. I'm going to stretch that angle by trying to work out the vertical component there. So I'm going to do 25 sine 35. 25 sine 35. 14.3. 14.3 is my vertical initial velocity. I'm going to go from 14.3 to a final velocity of 0 at the top with an acceleration of 9.81. So V equals U plus AT. This equation. My final velocity is actually going to be 0. My initial, I just said, was 14.3. My AT is 9.81 T, and I want to work out T. Take 14.3 to the other side and divide by 9.81, and you find that T is 1.46 seconds. That's half of that shape. That's going from initial speed upwards to no speed upwards. Double it. Double 1.46. You get 2.9. That's the answer. That is C. Another easy one. A girl bouncing on a trampoline, assuming air resistance is negligible, her acceleration is, and then you've got a load of options. Right. Anytime anything is in the air, whether it's a trampoline, a ball being thrown up, something falling, if the only force acting on it is gravity, that is called free fall. Okay, it doesn't matter whether she's going up from this trampoline or coming back down. The only force on her is gravity. That is an acceleration, so she can never have 0 acceleration. So it's not A, it's not 0 when she's at the maximum height. It is a constant when she's in the air, so the answer is actually B here. Acceleration doesn't change direction, that's why it wasn't C. Acceleration is always down. She can change direction, but acceleration is always down. And to say it's a maximum before she lands is nonsense. It's 9.81 all the time, so that is B. Question 8. For question 8, we've got this. It sort of seems like quite a horrific question. We've got this aircraft is moving or trying to move that way, but there's actually this wind blowing this way, not only slowing him down, but presumably moving him off sort of angle over here as well as he tries to go forwards. And you are asked, what is the time taken for the aircraft to fly a distance d due north with this wind taken into account? So it's actually a bit easier than it looks, this one. I want to know, what effect is this having on how quickly the aircraft is moving this way? So I want to work out this component of the wind, okay, this one, because that acts against V. Actually draw that on here. Right, so there's a bit of U, not U, like the letter U. CJ didn't double it, don't know what that means, but good. There's a little bit of this wind that's pushing back against the aircraft going forwards. Well, why am I singling that component out? Because that's the one that's relevant to the answer. I want to know the time this way, to travel a distance this way. So that is going to be U cos theta. You see, I'm going to crush that angle to get that component. U cos theta. So if I take V and I take away U cos theta, that's going to give me whatever V I have left this way. Okay, that's going to be a speed this way. But in the question, it wants me to have a time. Now, speed is distance over time. So distance over speed will give me that. These have all got distance over something. We want the one that's got V, take away U cos theta. So the answer for this one was A. So I'm just dealing with the plane going forwards and what's pushing it back. Number 9. Kind of easy, but kind of tricky at the same time, this one. So we've got a stone. The stone's being projected horizontally at a speed of 6 meters per second. So on your screen, it's being projected, and then it's going to do that. Okay, it's got 6 meters per second that way. When it hits the ground, it's going at 10 meters per second. How much energy is lost? And you can get to all the possible answers here by making a load of different mistakes. What we want to look at is all the types of energy. So initially, the stone has some gravitational potential, mgh, and it also has some kinetic. So we'll start with what it has initially. Let's clean this board. So initially we've got some potential, mgh. The mass of the stone was 0.4. G is 9.81. And h was 5 meters in this question. Multiplying those together, we get 0.4 times 19.62. That's not the only energy it has. That's potential energy because it's above the ground. It also has kinetic. Kinetic is calculated like this, half mv squared. So we've got half times 0.4 times 6 squared. Let's just type that one in. Half times 0.4 times 36, 7.2. Okay, so we add those together. That's the total energy it's got to start with. At the end, we're told that it's just going at 10 meters per second. It's at the ground, so it doesn't have any potential anymore, but it's going 10 meters per second. So do kinetic energy again, half times mass times 10 squared, and you'll find that that is less than the sum of these two that it started with. And it's less by 6.8 joules. which is why the answer is B. Finally, number 10. Now, this one does seem simple, but it's pretty horrible. Quite often when you get these questions, which of these forces can't be zero? Rephrase that. If these forces are all acting on a point, which set of forces cannot give you a resultant of zero? When you've only got two, it's easy, because what you're looking at is basically if they were acting in opposite directions, does one of them cancel the other out? If there's no way of doing that, then that doesn't work. With three, it's a bit trickier. Remember, for something to be in equilibrium, there's two ways we could look at it. We can think about the actual forces pulling on a point in different directions, or we can think about, do they form a closed triangle? And the first set you've got in that question is 3 newtons, 4 newtons, and 5 newtons. So you've got your 3, 4, 5 triangle, 3, 4, 5, once I caught the fish alive, triangle. We know a 3, 4, 5 triangle works, so those forces do add up to 0 overall. So it cannot be that one. 8, 8, and 8. I'm going to draw my point, and then I'm going to draw 3 8-Newton forces. If I'd drawn that accurately, would you not agree that those 3 pulling at the right angles would give a resultant of 0? So it's not that one. Finally, our last two are the tricky ones. Now, for our last two, I would say I can explain C the same way I did this one. As long as we have those two 10-Newton forces at pretty shallow angles, you can imagine that 2 10-Newton forces there, right, could just support a 2 that way. That works. You could draw it out in a proper triangle if you wanted as well. However, if you take the last line, pardon me, 3, 6, and 10, if you actually measure out a 3 centimeter line on a page, and then you look at 10 centimeters on your ruler, so you've got your 3 centimeter line here, and then you get your 10, and there's no way you could ever make a gap that was 6 centimeters. You can't make a closed triangle. And there will be more mathematical ways of working that out, but the thing is, these are multiple choice questions. They're quick ones. We've just got to eliminate the answers. So it's quite obvious that 3 of those will give you 0. You'll know what the answer is to the other one. If you want to check it, just try actually scale drawing that triangle. It doesn't work for D, so the answer was D. Thanks for watching. Any more questions before I go, just type them in the right hand side. If not, you will get your work tomorrow by email again. And if we need to do this again at any point, we will do. No, I think you've all fallen asleep. 10 likes though, genuinely more likes than I've got for any real videos I've done on YouTube, so thank you. No, I think unless we're very slow at typing. Oh, we've got Chris Lane. Bloody hell, Chris, really? Are you watching? Do we still have to send the answers for today? It's reasonably pointless because you can watch this over again and I've just given you all the answers. However, I have to keep a record of who's submitting the work, so I would suggest you do, because then you'll be on the spreadsheet. Any more questions? No worries, CJ, pleasure. Do the answers count towards your grade? Alicia, well, a couple of things. No, because this is work that I've set you and other teachers aren't setting the same work, so absolutely not. This is just so I've got some evidence that you're doing some work while you're at home. The other point is I don't know if you guys are going to get an AS grade this year because, of course, you're all going to do A2 anyway. The only reason we do AS is to give you practice of exams, really. So don't quote me on that, but I'm not convinced we're going to be getting grades together for you guys. I think you're probably going to do it like most other schools where you don't do the AS exam, you just do the A2 one. Thank God. Yeah, quite possibly. Right, enjoy your evening, guys, and I will see you soon. Bye-bye.